Well, hello everyone, that's the mathematical model of Bedini circuit. Well, as far as I don't know whether it's Bedini's or not, but everyone in the internet are talking about Mr. Bedini's invention, so that's the simplified schematic. Well, it's even more simplified here because you can't model the magnet passing through. That's another mathematical model that is on YouTube here, so you can watch it the way you have to make it. And I can give you a file. So let's get back to the model here. First of all, there's the scheme itself. That's the transistor, the diode that discharges the source of the opposite direction. There's the other diode that collects the back EMF into this capacitor here, and that's the voltmeter leveraged. I've got two oscilloscopes. This one, the A output is connected to the source signal, and the B side is connected to the coil here that will measure the consumption, the voltage of consumption, as well as the back EMF, the clear back EMF, the impulse. And this oscilloscope measures how much does the capacitor charges during the back EMF operation, which is cut through this diode. All these parts are identical to the scheme which was proposed by Mr. Bedini. That's the 8-volt battery here, 5-ohm resistor. Well, it may vary, but I found out that this is the optimal for this scheme. Of course, it's not the truth because it's just a mathematical stretch out of the whole idea. The signal here imitates the trigger coil of the passage of the magnet. It will be a steady state. It will increase the speed, because the nothing's ever taken here is just a schematic, electronic schematic. Well, 100 milliseconds of the one single impulse and 200 milliseconds for the whole window of an impulse. Now, we're going to start. Now it's a previous startup. Don't mind these letters. Figures will just start up and see what's going to happen. Well, the scale for this oscilloscope for the channel A, it's from the source here, is 10, let's make it, yes, 10 volts. No, let's make it bigger. 1 volt per single cell here. And the connection for the back EMF is, let's make it 20 volts per this cell. And for the A output of this capacitor here, it's 100 volts per this cell. Okay, let's start from 0. We have no current in the scheme flowing except from the battery here. So there's no current in this capacitor here. It's 0. Let's start. So it started. That is the input signal here. See? That's how it works. This impulse is a back EMF. Let me show you how big is it. It is about almost 50 volts back EMF with the input of there. It's clearly the input here is a minor. That's the input signal. This is the input signal. You see this step shaped. I will diminish it now, so I will just measure the back EMF. And we have a scale. Yep, right. Okay, let's minus there. Now, it's just a back EMF here. And the scale is 50 volts per cell, so it's almost 100 volts. That's the back EMF, this impulse. It's coming through the coil. There's 1, 2, 3, 4, so it means that there are 4 signals, operating signals from here, coming through this transistor, and as soon as it passes, the stored energy in the coil discharges. Well, the discharge of this energy is coming through this diode and charges the capacitor. How much? Well, that's how much exactly. It's almost 100 volts. This is the average voltage for 67 volts, and this is how it's true readings. Those are true readings. Well, what I should say that this is quite a good scheme. And it works, so we can verify whether what's the efficiency of this scheme. If we make another system here, and through the bridge, maybe through the rectifier, diode rectifier, and through the transformator here, I shall be able to recycle this energy and put a compactor here. Well, that's the future work. Now, as you can see, the process is growing and it charges the capacitor here. So it's pretty cool, it works, everything's correct. Now, I suppose that what we should do now is show the properties. As you can see, the scheme itself is absolutely identical to Mr. Bedini's. It's just a bit scrolled up because I made it in haste. The property of this transformator here is, let's see, it's got to be edit model, 600 turns. Well, I found out that this is really an optimum for the back EMF, or it is for 6,000 turns. The resistance of this coil is big enough, so the back EMF dissipates there, and the small number of turns decreases the back EMF. So that's almost the optimum, just as well as Mr. Bedini told us. As you can see, the voltage is growing here and here as well. Let's see on a bigger scale how it happens. There you see, there it goes. And here is the symbol, there. It's not zero. Just the scale is big enough, let's see. See, there. There's the back EMF here, and it's almost 2 volts only for the consumption. So it's pretty cool, right? It works, everything's fine. The compactor here is almost 100 volts in average. That's good. Well, I'll be keep on testing my mathematical model because I'm a lab engineer but a pretty good mathematician, so I'll be back to you. I hope with new results. So,